Okay, in this explainer, we're doing a high-level briefing, really a leader's guide on how to master the modern durability process. The whole idea here is to give you the strategic thinking you need to get products to market faster, but without ever compromising on safety or quality. And this is really the million-dollar question, isn't it? The pressure is always on to shorten those timelines, but you have to deliver something that's absolutely rock-solid and reliable. Well, the answer lies in a fundamental shift, moving away from reacting to problems and toward predicting them before they ever happen. And what's the payoff for that shift? It's huge. The OEMs who are really embracing the methods we're about to talk about are seeing a 40 to 60% cut in their physical prototype cycles. Now, this isn't just some small improvement. This is a total game changer for the entire development process. So, here's our game plan. We're going to start by rethinking what durability even means today. Then we'll put old-school testing head-to-head with modern simulation. We'll cover why correlation is absolutely essential for building trust, then dive into the wild world of advanced materials, and finally, we'll peek into the future with machine learning.
So let's start by rethinking the whole durability process. The stakes are just too high. We're talking cost, safety, your brand's reputation, to stick with the old build it and break it model. The future, the present really, is the virtual proving ground.
And this whole evolution is really a story of the old way versus the new way. It's about moving from these slow, incredibly expensive physical tests to a world of rapid, data-rich digital simulation. Let's break down that comparison.
And this slide really gets to the heart of the strategic advantage. Physical testing is reactive, right? You find problems late in the game when making changes is a nightmare, financially and time-wise. Computer-aided engineering, or CAE, is proactive. It lets us test ideas virtually, right at the beginning of the design cycle, and gives us this incredible wealth of data on the entire component before we've even made a single part.
But here's the crucial thing, and I really want to emphasize this. It's not about completely replacing physical tests. It's about intelligent integration. The modern process, like you see here, creates this powerful feedback loop. The virtual models tell you what to test, and the physical test data validates and refines your models. It's a single, powerful workflow. And that brings us to what is maybe the most critical step for any leader trying to build a CAE-driven process: correlation. This is the bridge that connects your virtual world to the physical one. Seriously, without it, your simulations are just pretty pictures. With it, they become your trusted guide for making huge design decisions. So let's be super clear about what we mean by correlation. It's the systematic, nuts and bolts process of comparing what your simulation predicts will happen with what a physical test actually measures. The whole point is to prove that your computer model is valid, giving your team the confidence to sign off on a design based on those virtual results. And this just illustrates the goal perfectly. On the left, you've got the CAE model showing where it thinks the high-stress hotspots are going to be. And on the right, that's the actual component sitting on a physical test rig. The mission is simple. Make sure the virtual prediction on the left is a reliable mirror of the physical reality on the right. Okay, so how close is close enough? Well, the industry gold standard for a good correlation is when your strain gauge data from the physical test matches your CAE predictions to within about 10 to 15%. When you hit that number, that's your green light. That's when you know you can trust your virtual models. And this is what success looks like. Check out this graph. You can see the line from the CAE simulation, our virtual data tracking almost perfectly with the data from the real-world physical test. That beautiful alignment is the proof in the pudding. It shows your model has real predictive power. All right, so now that we know we can trust our models, we can use them to tackle one of the biggest challenges in automotive design today: advanced materials. The constant push for lightweighting has brought in stuff like short fiber composites. And let me tell you, they bring a whole new level of complexity that demands our simulations get even smarter. And here is the absolute key takeaway for composites. With a traditional metal, the material properties are pretty much the same in all directions. But with composites, the manufacturing process itself, specifically how those little fibers line up during injection molding, that process literally defines the part's strength and how long it's going to last. I mean, just look at this graph. It shows you the problem perfectly. The green dots show the fatigue life when fibers are lined up with the stress. The blue dots, that's when they're turned sideways, perpendicular to the stress. The performance gap is absolutely massive, and that's something that only a really advanced multi-step simulation can predict accurately. So what this means is that our analysis has to become a multi-stage workflow. First, you run a molding simulation to figure out how those fibers are going to orient themselves. Then, you take that information and feed it into a structural analysis that knows the material is stronger in one direction than another. And only then, in step 3, can you put it all together to get an accurate prediction of the component's fatigue life. Now, looking down the road a bit, the next big accelerator is machine learning. It's already being baked into CAE tools as we speak, and it's set to make this entire durability process even faster and more powerful. Think of machine learning as a force multiplier for your engineering team. It's leading to things like real-time fatigue predictions. It helps create solvers that actually learn from past results and get more efficient over time. And it even embeds expert engineering knowledge right into the software. The bottom line? It makes the whole process faster and way, way smarter. So let's bring this all home. This isn't just about cool technology. It's about clear strategic advantages. A CAE-led process gives you speed, slashing prototypes by up to 60%. Correlation gives you confidence with a clear 10 to 15% accuracy target. Advanced simulation unlocks innovation, letting you use new materials with certainty. And machine learning, well, that's your ultimate accelerator. So, we've walked through the tools, the methods, the mindset. The virtual proving ground isn't some far-off future idea anymore. It's here, today. So the final question for you as an engineering leader is a simple one. How are you going to use it to out-innovate the competition and win the race to market?